Okay, so here we have a problem that deals with electric and magnetic field forces. And we have a couple different regions and things going on. So we have one region where there's both an electric and a magnetic field. And I've drawn the electric field in blue and the magnetic field in green. And so the electric field points toward the top of the page, and the magnetic field points up straight out of the page. In the second region, there is only the magnetic field, same as in the other region. And so our first question is, at this point right here, point P2, what's the direction of the force on the ion? And we don't know if it's a positive or a negative charge. And since we don't know that, we can't use the right-hand rule to figure out the magnetic force and the magnetic field. But we do know something else. We know how it moves, and specifically the direction in which it curves. And so because this little bit right here is a circle, or half a circle rather, we know that the acceleration that must exist is a centripetal acceleration. I should clear that, it's a little bit messy. So since we know we have a centripetal acceleration, we know what direction the acceleration must be in. It must be towards the center of the circle, right? The center of the circle is about there, roughly. So we need a centripetal acceleration there. But because of F equals ma, if we know the direction of the acceleration, we also know the direction of the force. It must sort of point up and to the left, towards the center of the circle. So anything kind of like that. So that's part A. Part B is now we know the direction of the force. From that, tell me if the ion is positively or negatively charged. So this is where we're going to use the right-hand rule. So thumb is the direction of motion, right? So that's like this is the QV part, right? That's assuming it's positive. If it's negative, right, this would be like a negative QV, either one. But either way, we know the magnetic field is out of the page. So thumb is pointing either in the direction of the red or the blue, depending on whether it's positive or negative. That's what we're going to answer. Index finger points up. And then our middle finger will point in the direction of the force. And so if we do those things, the right-hand rule, this is like F if it's positive, it points that way. And this is F if the charge is negative, it points that way. Right? That's how our fingers have to line up to make it work. And since we know this is the right direction, right, now we know it must be a negative charge. Right? That is the correct one. So we know we have a negative charge from the right-hand rule. All right, so we've done with region 2. Now it's off to region 1. We have another point right here, and you have to figure out the forces that act on the ion at that point. The magnetic part hasn't really changed, right? We still do the right-hand rule. Now we know it's a negative charge, so we have, right, QV. Make sure we draw that a little bit more cleanly. Right, so for the magnetic charge, QV points that way, right? Opposite the direction it's moving in because it's negative. That's our thumb. Index finger is out of the page, and so our middle finger, the force, is going to point like that, right? And so this, right, is the magnetic force. That's labeled number 1. But now we've introduced an electric field. Fortunately, though, the electric field is a lot easier. Since the charge is negative, the force is the exact opposite direction of the field, right? So, there. And those are our two forces. I'm going to redo that to be a bit neater. Because it's moving in a straight line at a constant speed, we also know that these two arrows have to be exactly the same length. Right? You should make sure to draw that. All right, and finally, a calculation. We have to figure out how fast it's moving. So for it to move at a constant speed, right, what I just said, these two arrows are the same length, right? Or the net force is 0. That's no acceleration. That's what a constant speed is. So that's the expression that has it. The two forces are equal. And we have an equation for the magnetic force, QVB, right? That's the magnitude. We've already calculated or done the right-hand rule to figure out the direction. And the electric field, or electric force is just QE. So the Q's cancel, right? The charge of the particle actually does not matter. And we're supposed to solve for V, so I divide both sides by B, and I get a nice and simple result. That the particle must be moving at that speed for it to have a constant speed without change in direction at all, right? And we're allowed to use E and B because we know the magnetic and electric fields from the earlier part of the problem. And so that's it.